eyes in the classroom and you help me prioritize what it is that we should discuss. Fair?
Yeah.
Okay. What should we discuss today?
Um, I know we have a quiz. It's supposed to be on Wednesday.
Mm-hmm.
Um, it says on chapters 5.1 to 5.3
Mm-hmm.
of the textbook, but we haven't even started the unit yet,
Got it.
so I don't really know anything from that.
Okay. What's 5.1 through 5.3? What's 5.1 and then what's 5.2 and what's 5.3 about?
I'll get the textbook.
No worries. Tired?
Sorry?
Are you tired?
No, I'm fine.
Okay. Oh, by the way, how's your sister and what is she up to these days?
Maddie?
Yeah.
She's good. She's in her senior year right now at college.
Okay, cool. UPenn, right?
Yeah.
Okay. Yeah, I worked with her briefly a few years back.
Yeah. So 5.1 is areas and distances,
Mm-hmm.
integrals or something.
Mm-hmm.
And then 5.2 is the definite integral.
Mm-hmm.
And then 5.3 is evaluating definite integrals.
Okay, got it. Okay. So, sorry. Um, did you have certain questions that you wanted to go over?
Well, we haven't even started the unit yet, so I don't really know anything about this.
Okay, no problem. So, yeah. So, what does the word integral mean to you?
I have no idea.
Okay, it's okay. So it's really cool. So an integral is like the area under the curve. So the symbol for it is this, and so let's say that you have x cubed and then dx. So there'll always be a dx. There'll always be an integral symbol. So the integral symbol is like this elongated s, and so what you're doing essentially is like going backwards on derivatives. So like if I said you have x to the fourth, and I say find the derivative of that, how would you find the derivative of x to the fourth? So in writing ddx, I mean derivative. So what's the derivative of x to the fourth?
4x to the third.
Exactly. So 4x to the third. Exactly. Good job. So what the task at hand when you're doing integrals is you're trying to go backwards. In other words, the question you're asking yourself is, what is this the derivative of?
Oh, so we're doing antiderivatives.
Exactly. Exactly. So what's that?
Um,
You got it.
Yeah, I just did. We had the unit test last week,
Uh-huh.
and antiderivatives were on it.
No worries. No worries. So, like in general, if you have an expression that looks like x to the n, like obviously the derivative would be nx to the n minus 1, because you did that successfully over here. So when you go back, what you do is, so if I asked you for something that looks like x to the n dx, what you would do is you would add 1 to the power and going backwards, and then you have to divide by that power. So it's x to the power n plus 1 divided by n plus 1. And it doesn't matter whether or not there is a constant in front of it. So in the task I assigned you, I didn't put a constant there. So there could have been a 2 here. You ignore that 2 and just take care of this part, which is adding 1 to the power and then dividing by whatever the new power is. So granted that, let me go back. Granted that, what do you think now is the antiderivative of x to the third?
So it's x to the fourth over 4.
Exactly. There you go. X to the fourth over 4. Excellent. Now, what if I had had a 2 right there? How would you have modified your answer?
1/4 x to the fourth.
Yeah, you'd keep this 2
Or
and then
1/2.
exactly. No worries. Everything else would stay the same. Now, what is it? Maybe your teacher or the sub reminded you. What is it that when you're doing antiderivatives, what is it that you mustn't forget at the end?
The plus C thing.
Exactly. Plus C, because, well, let's set aside the 2 for now. Like, we saw, like, how our answer would be different if there was a 2. It's only slightly different. Now, notice that, like, it doesn't matter what I would, by the way, sorry, you can see what I'm writing, right?
Yeah.
Okay, great, thanks. So it doesn't matter what that constant is. Like, I could have, instead of the plus C, I could have, like, put a plus 3. What would the derivative of this be?
4x cubed times
4x cubed.
4.
4x cubed, and then the constant, though, this is dividing by 4 is really the same as multiplying by 1/4, so we retain that. It's really a constant in front of the x to the 4th. So just as we had done with the 2 when we're doing the antiderivative, we just kind of ignore it. In other words, what I'm saying is, like, if I so chose, I could see x to the 4th over 4 as 1/4 x to the 4. Now it becomes a lot, and of course I had the plus 3, it becomes a lot clearer that that 4th was kind of like the 2 we had there. So we ignore it and we take care of the rest of it. So then in the process, we just retain that 4 in the denominator. And what happens to the plus 3 when you take the derivative?
Goes away.
Exactly, it turns into a 0. The derivative of a constant we know is 0. So it wouldn't have mattered if that 3 was a 5, whatever. Like, so we got to put a plus C, like, because, well, we see that, like, without additional information, we may not be able to determine what that constant is, but regardless of what constant it is, negative or positive number, it would disappear when we taken the derivative. So that's an indefinite integral. So an indefinite integral is the same as antiderivative. So some of the stuff that you got to kind of, like, deal with is the terminology, right? So antiderivative, I'll write it up top. Antiderivative is synonymous. This is identical to indefinite integral. They're one and the same. So what you're doing then is, like, this kind of a deal, right? Like, so, like, just to get our feet wet more on antiderivatives, I'll, like, say a little, give you a bit more additional practice. Yeah, by the way, like, if you feel that, like, I'm over-explaining something or whatever, like, feel free to interrupt and chime in anytime you want. It's perfectly fine to interrupt me and be like, I got it. Okay, sorry. Okay, so let's say that I this time gave you, like, 3 x squared and then plus like, plus square root of x dx. So what would you do here?
Taking the antiderivative? So it'd be 3 x to the 3rd over 3.
Beautiful.
Plus x to the 3 halves over 3 halves.
Yeah, very well done. Yeah, because exactly, excellent. So you know a lot more than you're leading me on to believe. Like, you're, like, pretty good. So good. Like, all right, very coachable. Great. So obviously, you want to do a little bit of tidying up here. Like, dividing by 3 halves is the same as multiplying by 2/3. Blah blah blah. So, like, obviously we clean this up like that, and then it'd be like x cubed and then plus 2 over 3, and then x, the square root of x cubed. That's what we mean by, like, x to the 3 halves. And this thing that you write right here in square roots is called an index. That's like TMI. Like, and so when it's square root, we don't bother writing it, blah, blah, blah. Okay, and then our plus C, we're done. Okay, good. I'm very happy about, like, how well you understand your antiderivatives here. So, like, the only thing different between antiderivatives, general antiderivatives, which are also known as indefinite integrals and definite integrals, the only difference between them is, well, then when you're dealing with a definite integral, so we're now on 5.2, you got to put a number here, let's say 0, and a number, like, well, let's make it more interesting than 0, because 0 annihilates everything. Let's say 1 here, and let's say 3 here, and so then let's say that, like, it's 3x squared dx. Well, like liking these numbers too much. So let's say 5x squared dx. Well, okay, so it's just like an indefinite integral, just like what we were just doing, only like this time there is no plus c, and you gotta plug in the numbers here and here at the end. I'll show you how to deal with them. Maybe you already know a little bit about them. You can tell me. So the two numbers that go on the bottom and the top of the integral sign are called limits of integration. Okay, so talk to me. How would you deal with this? Well, just get me started.
5x to the third over 3.
Beautiful. 5x to the third over 3. Now, the only thing you do differently this time is you put a vertical bar here, meaning you are about to plug in the limits of integration. And so there's a 1 here, there's a 3 here, and you plug them in the order of the number in the top. So 5 and then 3 cubed over 3, and then so there's a bit more number crunching, and then 5 thirds, and then well, we plug in 1, so 1 cubed, and obviously we simplify here, and when it's all said and done, like, we get a number out of this. So we get 5 times 3 cubed is 27 over 3, and then minus the 1 cubed is just 1, so we get minus 5 thirds, and this here cancel into a 9, so we get 45 minus 5 thirds, and we could like simplify this number, blah blah blah. Okay, now any questions as to what I just did?
No.
Okay, great. Now, so there is a geometric interpretation of this, and that's what's really cool about calculus, right? Like, so, like, what is it? In geometry, you can only find the area of things that are like boxy, like triangular or rectangular, blah blah blah. And what calculus allows us is the freedom to find like areas of more interesting things. So what we've just figured out with this number right here, the meaning of this number, right? What's that? Like 45 minus 5 thirds. I don't know. We can simplify it, but like 135 minus 5 over 3 is what it would simplify to. That's 130 over 3. We both know that's roughly like 40 and change. So what that represents is this, bud. So like suppose that we graph the function we took the antiderivative of. So the definite integral of. The function we took the definite integral of is this function right here. What kind of a function is that?
Parabola.
Exactly, beautiful. So it's a parabola, and I mean you're a student from Hackley, so I knew like you had like really good training. Good job. All right, so yeah, you know all the things that I would require that you know. Good. So like we know it's a steep parabola because, well, the 5 makes it climb faster. Blah blah blah. All right, got it. So then now what you and I just did is we found like, so this lower limit is telling us the cutoff on the lower part. So this is 1, and then this is, let's say, 3. Then what you and I just figured out is the area exactly under the curve, under the parabola, between 1 and 3. And so the area bounded by the x-axis, and then the parabola from the vertical line x equals 1 to the vertical line x equals 3. That's the meaning of this number right here. Make sense?
Yeah.
Okay, so that's all a definite integral is, and that's how it's different from an indefinite integral. So when you're figuring out an indefinite integral, you're just figuring out what function did I take the derivative of, and they may be like vertical shifts of one another. Because like, well, let me explain that a little bit. Like, so why? Well, sorry, hold on. Yeah, I'll do that. So, the reason why the plus c when we're doing indefinite integrals occurs is, remember, what does a derivative really mean? What are you finding when you're finding? So we just learned that a definite integral, what it means is area. It literally means area. So what does a derivative mean? What's a layman's name for a derivative?
slope.
Exactly. Beautiful. That's right. So like consider the derivative exactly. So consider the derivative at x equals 1. Let's say that this is x equals 1. Well, so let's say that you're dealing with a cubic function. Well, this may be like what I just drew, maybe x cubed plus 2. If this right here is 2. And let's say that like I have this function which is identical to it, but right here is negative 1. Well, this time, so this is x cubed plus 2, and this one is x cubed minus 1. Well, fine. When we take the derivative, we know this the constant disappears, blah, blah, blah. But the derivative for both of them is 3x squared because, well, that's the slope at x equals 1 for both is the same. They're simply vertical shifts of one another. And so that's why, like, what you're doing is you're trying to figure out the parent function whose derivative you took to, to have it stuck inside the indefinite integral sign, but like clearly like since derivative means slope, blah blah blah, like you get it. But whereas like now, like we move to definite integrals wherein like, well, this time we mean area. And so like here's a question to you. Why is it that like when I was showing you how to do a definite integral, we didn't have a plus c? Why do you think that happened?
Um, because it gave you what to add already.
Say that again.
It gave you what to add.
Sure. Here, I'll explain it slightly differently. So, like when we had 1 and 3 here, let's just as we had done with indefinite integrals. Let's say that we like do 5x cubed over 3 plus c. Well, when we're evaluating, we're plugging in 1 and 3. Well, we plug in 3 first, so we have 5 times 3 cubed over 3 plus c. But then we do minus what we get when we plug in 1, so that it'd be 5/3 and then 1 cubed plus c. Well, now when you execute this to simplify, what happens to the plus c over here and the plus c over there?
You cancel out.
Exactly, exactly. Well, so it's really because of the geometry. Let's see, sorry. That like the we don't worry about the plus c, and I'll say more about this on a future session. But for now, this is good enough. So evaluating definite integrals, yeah. So this part right here is simply about like it's the same as evaluating is like plugging in these numbers and in the end getting a number out. That's all 5.3 is. So 5.2 and 5.3 are not very different. So all you would need in 5.3 is a lot more practice. And I just so happen to keep like my worksheets from all those years back, and like I have taught more calculus courses elsewhere. Do you know St. Anne's?
St. Anne's.
Uh huh.
Yeah.
Yeah, I taught at St. Anne's for 4 years. So I taught Calc BC, blah, blah, blah there. So I have a lot of worksheets. That's all I'm trying to say. And so, like, whenever you need additional practice, we'll have an abundance of them. But yeah, like, all 5.3 is like practicing this stuff more. Now, 5.1, like, area and distance as well, we get what the area is, right? Like, so I'll say a little bit more about 5.1. I know, like, what's intended and why it's in a separate like section than 5.2 and 5.3. So I'll say a little bit more about that in a second. But for the distances part, can you like take a picture of 5.1 and like the exercise pages and also like the first couple of pages of it and text it to me?
Yeah.
Okay, thanks.
Just the exercises, right?
Yes, sir. What kind of grade are you maintaining right now?
First trimester I got a B. This trimester we just got the mid trimester reports, and I have a C plus / C right now.
Okay, like I mean, quite honestly, like I can get you to an A. Like, you seem like a wonderful student from what I can tell, and like a great listener. And as long as you do that and you execute, like we can get it to an A.
It's just been really tough to like pay attention online.
I understand that.
And especially when it's like the entire like I'm the only one online, and then there's like they're teaching the entire class in person,
Ooh.
and then like the like camera you can't even see the board, so it's like I might as well just not pay attention and look at the note sheets Mr. Clark has.
Yeah. I'm sorry. Wait. So like, why are you the only one not online?
My parents just don't want me to go in.
I understand that. Yeah, I have another Hackley student, and like her mom also the same. Like she doesn't want her to go.
Yeah, there's like 2 kids online, and then it's like I don't know, 14 kids in class, and I'm like, okay, I can't really.
Yeah. Sorry. So find it. Okay, got it. Are you using Stuart?
Am I using what?
Is the book you're using Stuart?
James Stewart, yeah.
Okay, gotcha. I have a copy of that book. So, like after today, I should be able to. Sorry. Uh, use 6 rectangles. Gotcha. Like, all right. This makes sense. So, I want to teach you a couple of ideas here. So, like on 5.1. So, one of them is like this, right? Like, so, like, let's say that like you have to find the integral of the square root of 9 minus x squared. Now, like you see, like earlier, like we saw, well, if it was simply 9 minus x squared, and let's say that this is from like 0 to 3. So, and let's do the same task, but like on the simpler guy right here. So if we're doing it on the one on the right, like I think I need to have a dx here, but I think you know what to do. So talk to me.
So it'd be 9x
Mm-hmm.
minus x to the third over 3.
Beautiful.
And then, do you add that, or like for the 3 and the 0 thing, is it addition or subtraction?
Yeah, it's subtraction between them, and this vertical bar is saying that like you're about to evaluate, and you need to have it as soon as you write this part. You need to have your vertical bar, and then the 3 on top, the 0 on the bottom, and then in the next step, you could plug them in and execute. So talk to me.
So 9x minus x. Yeah, so 9 times 3 minus 3 cubed over 3 minus nothing.
Yep, exactly. 0 minus 0. Got it. And like obviously, like goes without saying. Sorry, I sometimes I'll like out of paranoia of like desire to like take care of small details. I'll say things that you might know, but you might already know. But obviously, we need the parenthesis because there are 2 terms, and we need to distribute that minus sign. Okay, but in this case, it doesn't matter. Anyway, okay, so you get number out. This is pretty easy. Now, this here is not an elementary function. By the way, what grade are you in?
I'm a senior.
Okay, got it. So, sorry. So, like, I'm sure when you get to college, you'll do more advanced definite integrals like this one, where you'll learn the technique to actually, like, find the antiderivative. But in Calc AB, you don't get to learn the technique. What you have to do is understand this function geometrically. So, in geometry, what this function is this, right? So, it is a circle because for this function and this function, we're really talking about y equals. So if we take y equals and then square root of 9 minus x squared, then like what we could do is square both sides. So what you get is y squared is equal to, when you square both sides, you get y squared is equal to 9 minus x squared, and then we add the x squared to both sides, and then we get x squared plus y squared is equal to 9. Do you recognize that as circle?
Yeah.
Yeah. Talk to me about what kind of a circle.
Circle with a radius 3 and origin at the 0, 0, 0, 0.
Beautiful. Like I'm so like happy with like your mastery of the fundamentals. Great. So yeah, 3 there, 3 here, -3 here, -3 here. And so, well, we know how to draw circles, just like do that. And so obviously because there's no minus sign here, right? We're not talking about the bottom half of the circle. So if it were a minus sign, it would have been talking about the bottom half of the circle. But because there is no minus sign, it's automatically suggesting that it's a positive. And so then we're talking about the top half of the circle. I'll highlight it in green. So here, what we're talking about is this fella right here, right? And so then what's asking you is the area, because now we know that when you put these numbers in, it means that we're finding area. So specifically area between the function this time is a circle, and since we're concerning only 0 to 3, we're talking about this quarter circle's area bounded by the x-axis and the circle's curve from 0 to 3. And so then now you could just do pi r squared, which would be pi times 3 squared, because it's a circle of radius 3, and divide that by 4, because we're doing a quarter circle. That would be your answer for this. Now in Calc BC, and I'm sure you'll take more math in the future, when you do that, you will learn like this like really convoluted long way to get to the same answer, which is like pi 3 squared over 4. You'll get to the same place, only like you will instead of interpreting it as a circle, you will actually like learn the technique by which you can find the antiderivative of the square root of 9 minus x squared. But we don't need to worry about that. I remember like in my years of teaching this, I imagine that you'll be taking the AP. We had to explain the geometry interpretation of some of these like these items like circles and triangles, blah blah blah. Obviously, you know what's the difference? Well, let me, instead of saying obviously, let me ask a question. So let's say that this is like 3 here and this is 3 here. Can that be possible? No, that'd have to be 6 here, right? Okay. No. Okay, sorry. Poor numbers. 4, or 2 and 4 here. All right. So let's say that, and then I have this here. Sorry. This is a very typical calculus AP question. So let's say that this here is like 8, and let's say that this is 10 figure now drawn to scale, and this right here is 3, the peak of this triangle, and this right here is -3. Now, if I asked you to find the for this function, obviously it's a piecewise function because in parts it's a circle, it's a semicircle to be specific, and then it's got straight line parts, blah blah blah. Now, but I could still say it's a function f of x, and I ask you to find the definite integral from 0 to 10 of this function that I'm calling f of x dx. Well, we know now that a definite integral means area. So what I'm asking you in writing this is I'm asking you to find the area between 0 and 10. So talk to me about how you'd go about that here.
So do you just split it up into the semicircle and the 2 triangles?
Absolutely.
So to find the area of the semicircle, it's 2 squared times pi over 2.
Yep, there you go. Beautiful.
And then the triangle would be 1/2 base times height. So 1/2 4 times 3.
Yep,
and
beautiful.
Then the triangle is going to be 1/2 2 times 3. Will it be, do you use -3 or?
There you go. There you go. That's the only reason I pose this question, is for you to understand that there is such a thing as area, a negative area, and that's when it's below the x-axis. You already figured it out. Beautiful. Very well done. And obviously the rest of what we have to do is like, you know, simplify this and whatnot, and for that you don't need me. You could do that on your own. Okay, cool. So these are kind of like the brief things that I wanted to talk about in 5.1 from what you texted me. I like glanced at it, and but we need to.
Yeah.
Claudia.
Yep.
Okay. She's funny. I really like her. Sorry. I asked her one time, like, because she's like brutally honest. I'm like, Claudia, as you get older, like, will life gets easier or harder? She's like, definitely harder. Sorry. So like if we return back to like this here, 5x to the third, like dx, and we still have like 1. So we saw that you get that. What was it that we got? Like 130 over 3, something like that.
Yeah, 130 over 3.
Now, like before right now, because it'll be useful. 130 over 3. Before you learn that, like how to find the exact area, what happens is you could approximate the area, and here's how you do it. So like, well, you'd want to draw an accurate graph of this guy, 5x to the third. So I'm gonna draw a semi-accurate, like, but like exaggerated, like graph of it, because for what I'm about to do, it's important that I draw it exaggerated. Okay, so like let's say that this is 5x cubed. We know it's traits blah blah blah. So like at 1 it's 5 blah blah blah. So like let's say that this is 1, and so then as I just said, like the corresponding y value is 5. And what would the corresponding y value be at 3?
27 times 5.
Mm-hmm. Yeah, that's a lot. Sorry. Maybe like I'll like just for the sake of
135.
yeah, I apologize for talking over you. Now hold on. Just for the sake of demonstrating, like let's like work with a nicer function. So hold on. We don't need to get bogged down on the numbers. Okay, so let me just make you evaluate 1, 2, 3, and since you know the ropes a little bit now, you've got it. And it's simply x squared dx. It'll suffice to demonstrate the concept. So, well, talk to me.
So we got x cubed over 3.
Mm-hmm.
Yeah, and then you get 3, so 9 minus 1. So 8.
9 minus
1.
1.
Oh, over 3.
Yeah, you got it. No worries. So that's 20. You got it. 27 minus 1 over 3. That's, I believe, 26 over 3. What is that? Like 8 and change. So let's say 8 and change. 8 and change. Okay. I'm being lazy. We can figure it out. It's like 8.67. Okay. Sorry. Okay. Now, like, so this is the exact area for the function. I'll keep my drawing and I'll just call it like x squared. So this is the exact area for x squared. Well, this time we know at 1 it's 1. At 3 it's 9. So the number we just wrote down is the exact area above the x-axis, below x squared, from x equals 1 to x equals 3. Got it. Now, before you learn like how to do this, which is antiderivative, then plug in, blah, blah, blah. Before you learn that, you are taught to approximate the area. And this is definitely a question you're going to see on the AP come AP time. Now, approximating area. So there are a few ways to approximate the area. They're generally called Riemann sums. Riemann sums. So this means area, rectangular approximations of area. So I'll write it. Rectangular approximations of area. Okay. Now, so years ago, like I think, yeah, I tutored a kid who's like third in America in squash. Like for his
Who was it?
shoot, Michael Rupert. Like I think, yeah.
I have never heard his name before. I was I was 3 last year.
That's amazing. Wait, sorry. Like they were twin brothers, but they did look like each other. Maybe I like calling the non. I will ahead of our next session, like because I have emails from him. I'll look it up because yeah, sorry. I think Michael is his brother because you would know. Anyway, sorry. So getting back. So rectangular approximations of the area. That's amazing. Good job. Being that good at anything is very like cool. Sorry. Yeah, of course. So rectangular approximations of area, right? Like that's what Riemann sums means. Well, okay, fine. So like how do we approximate the area using rectangles? Well, there are a couple of questions. One is like how many rectangles do we divide up the area into? So like usually so you're told left and then right Riemann. So like it's implicitly understood anytime you're doing rectangular approximation that you are talking about Riemann sums. But then other than that, like the word Riemann sums doesn't come into play. What you're gonna see is L and then a number. So if it says L2, it means use two rectangles but left approximations. What do you think that means, left approximations, as opposed to R2, which is right approximations and use two rectangles?
Starting from the left.
Yeah, sure, exactly. I conveniently divided up the area we need to approximate, which is from 1 to 3 under the curve, blah blah blah. I divided it up into two nice like parts. But then now like if I draw my rectangles so that the height, like, so I have an interval from 1 to 2. Well, from 1 to 2, I'm asking myself, well, do I use the height of the rectangle on the left, or do I use the height at like 2, or do I use the height at 1, basically, right? If I articulate myself better. Well, okay, so when it's left, you use the one on the left. So you use the height at 1 when you're considering the interval from 1 to 2, and then when you're considering the interval from 2 to 3, you use the height at 2. Like, fine. So then what do you think it will mean when we're doing right 2?
Use the height on the right.
Exactly. And if you could use your mouse and draw me that. So I don't know if you're, yeah, go ahead and draw it. Like the right
Can you see my mouse?
Huh?
I don't think I can.
Okay. Well, okay. I'll make sure that you're enabled here. Well, I'll figure out like how to get us back, get the Flash stuff fixed so that you're on the site. Anyway. So we probably won't be here, but if we have to be here, I'll figure out like how to give you access. I know you can give students access. Anyway, I'll draw it in green here. So for R2, it would be this rectangle and then this rectangle. Well, okay. So let's find L2 and let's find R2 in this specific example. And the function again we're working with is x squared. So talk to me.
So it'd be 1 times 1 for the area of the first one.
Yep.
And then 1 times, what's the height at 3? 6?
The height at 3 or the height at 2 for this second rectangle in blue?
Oh yeah, the height at 2.
No worries. Yeah. Okay. So then.
That'd be 4.
Exactly. Beautiful. 2 squared or 4. Got it. So if we calculate this, that turns out to be 5. Okay. Got it. Now, what about for R2?
1 times. Oh. So 1 times 9.
Let's work. It's okay. Let's work on this one first. This rectangle.
So 1 times 4.
There you go. Good. And then
1 times 9.
Exactly. Plus 1 times 9. Exactly. So we with the width of the rectangles is convenient. Is simply 1. Blah blah blah. Okay, fine. If we calculate this, is 1 times 4 is 4 plus 9 is 13. Got it. So we have 13 and 5, and the true area is exactly between them. Well, duh. Like one of them under approximates the area, and the other over approximates it, and the true area is, no surprise, somewhere in between. Fair?
Yeah.
Okay, got it. Now, question: does left Riemann always under approximate and right Riemann always over approximate?
No.
Why not?
So the function can change.
Exactly. Say a little bit more.
I mean, if you just flip it.
Exactly. So the function needn't be an always increasing function like I drew. Like, so if the function was decreasing, they would actually swap roles. The left one would over approximate it, and the right one would under approximate it. Fair?
Yeah.
Should I draw that? You're good.
I am good.
Okay, good. All right. Great. So like we know the exact area is 8.67, and as we expected, one of them over approximates, the other under approximates. And we don't need to say more about that, but here's a really cool part. Well, remember, like the little numbers underneath L and R, like they tell you how many rectangles to use. So, oh, sorry, I didn't mean to do that. Hold on. Like they tell you how many rectangles to use, and if I increase the number of rectangles, well, obviously the computation would be a little bit more cumbersome. So, like, let's say that this is R. Sorry. This is R4 and L4. Well, we're dividing it up into more rectangles this time. And so, what general comment can you say about the approximation if we divide it up into more parts?
Maybe more accurate.
Exactly. For our specific function, the left Riemann, which is what I'm drawing, still will under approximate it. But without us having to labor through the calculations, it's pretty obvious that the number is going to be more than 5, and it's going to get closer to this number, like the actual area. And same with our right approximation. We'll still over approximate it, blah, 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 but like it'll be lower than 13, blah, blah, blah. So if in theory we use infinitely many rectangles, it will be the exact area. And that's actually like how you get to like this. We learn that like what you do is like really x cubed over 3 and evaluate it, blah, blah, blah. Okay, so you learned about left and right, and so there's two other ways to approximate area. And these are also very popular on the AP, so I'm sure as Hackley cares about their success on the AP, they will want you, yes, they will want you to know this. I was really young when I was teaching at Hackley, so I was like a total clown. Like there was a kid who was like the kids just walked all over me. I taught it twice. Like the second time, my kids did really well on the AP, but the first time was like mediocre. Like there were a few kids who were like dedicated and got 5s, but like there were a lot of smart kids that got 3s and 4s because like they were just like clowning every day, and I didn't know how to stop them. Sorry, hold on. Yeah. Sorry. So. Like there was one kid, like really awesome kid. He's a banker now. Like what is it? Went to Chicago. Blah blah blah. He was sick, and we had to like kind of like the way you're doing. We had to teach him on camera, and like every day they were like they missed him, and they were being so goofy. Like you couldn't tell there was an adult in the classroom.
That was like my bio class last year.
Yeah.
Do you know Miss EK?
Of course.
Yeah, so she was gone last year, and then we had a sub for like the first trimester, and it was basically just everyone got an A, and you could go up there and you like act like you're so sad, and you're like, oh, like everyone's getting an A. She's like, okay, fine.
That's funny. Sorry. So. Let's say that this is 2 right here. Now, like we're going back to the same function x squared, but this time we're learning about another type of Riemann sum. And this one is called the midpoint. So again, like it would be like M2, M4, blah, blah, blah. Prescribing the number of rectangles, but the M telling you that what you're using is midpoint rule. So midpoint rule is like surprise, surprise. Like, what do you think it means?
You just take the height at where the middle of the rectangle would be.
Absolutely, you got it. Beautiful, very well done. Okay, so the height would be like at 1.5, 3 halves, and then I believe this is going to be 5 halves, and I'll draw the rectangles. Like so, the rectangles are gonna look like this now. And so, oh no, that's the wrong spot. Sorry, my bad. Right here. Okay, got it. So now look here. So look at this part, right? Like on over here, it under approximates it. Over here, it over approximates it. So what general comment can you have about like the midpoint rule?
It like kind of like tries to eliminate the over and under approximating things.
Exactly, beautiful. So you could decidedly say without proof that midpoint is a more accurate rule than left or right. It will always be that will always be the case whether whatever the function may look like. It will always be a better. It will always do a better job at like finding this number than either of the previous two. Let's actually like just for the sake of satisfaction go through it and yeah. Okay, so um sorry. And so talk to me about using the midpoint rule to approximate here and here.
It's gonna be 9/4 plus 10 plus 25/4.
9/4 plus beautiful 25/4. Great. What does that come out to? Like if we add 9 and 25 is 34. 34/4. What's that roughly?
8.5.
Okay, exactly. That's darn close to like the actual value. Great. And there's one other one, and sorry. So we could maybe conclude on this one. So so the other one is this, and this one is called the trapezoid rule, and you take a wild guess, but it means that we're using trapezoids to approximate the area. So they don't usually use T, but they'll just spell it out as saying trapezoidal rule. Okay, sorry. So for the trapezoidal rule, if we return to the same function, x squared, then like again from x equals 1 to 3, and then like yeah, just for the sake of practice, here's 2. Like so we're using a trapezoid now. Like real quick, like if I have a trapezoid, we usually like see a trapezoid sitting like this. You have what's usually called base 1, base 2, and height. What is the area of the trapezoid?
It's the average of the two bases times the height, right?
Beautiful, yes. B1 plus B2 over 2 times H. Exactly. So that's what you'll have to do. Now, there are some kind of like nice things, that, right? Like, which is like, well, first of all, if I draw my trapezoid this way, so first, there is my first trapezoid. Here's my second trapezoid, and if I also find the height. Okay, now let's call our function, well, it's x squared, we know, but let's call it f of x. Then what is going to turn out to be true about f of x here? So, like, well, first, we use the average of the bases, right? So I'll have to do f of 1 plus f of 2 over 2. That's for the first trapezoid times what?
1.
Exactly, times 1. And like usually the width of the rectangles, notice that we always conveniently divide the rectangles so that the widths are the same. They're a change in x, so they're called delta x usually. And yes, we know delta x, the change in x for the width of our rectangle this time is just 1. But yeah, I have a delta x there. Like, sorry. So I was just like grocery shopping and whatnot, like right before your session. I had my mask on. I'm sitting here tutoring you with a mask on. I have no idea why when there's no one else here, I'm wearing a mask. It's become a reflex. Anyway, talk to me about the second rectangle, which is this rectangle right here.
F of 2 plus f of 3 over 2 times delta x.
Exactly, f of 3 over 2 times delta x. Now, I intentionally wanted to approach it this way instead of number crunching because, well, look, there are a number of conveniences, right? Like, first of all, I'm quite certain that you're good enough at arithmetic to where if I instead of dividing by 2 there, I divide by 2 here. You're not going to be confused. And I could do the same here. I could relocate this 2 over here. So for starters, delta x over 2 is common. It's really 2 terms I have here because I'm using only 2 trapezoids. But in both situations, there's a delta x over 2 involved. And that will always be the case. And then f of 1, that's the leading x. That's not repeated, but notice that f of 2 will be repeated. So it's f of 1 plus 2 f of 2. And then the last guy, f of 3, is not repeated. And like, yeah, this is not of tremendous value right now, but if you're using a lot of rectangles, it makes a big difference. So what happens is the first x value is used only once. The last x value is used only once. Every x value in between, when you plug it into f, that's used repeatedly. So it'll be double every x that's between the first and the last one. And once you compute all of that, you have to multiply all of it in front by whatever the change in x is divided by 2. Fair?
Yeah.
Okay, cool. So, but I think the only thing you need after this is like additional practice on this stuff. So, like as like a first session where we, touch base and one, like kind of diagnose like, like the things that you need to learn, and two, like, just learn a little bit about each other and how we work, blah, blah, blah. Like this, like I think this is a good first start. And like I said, if you need additional practice, I have tons and tons of practice, including like practice tests and such. But before we conclude, because we started a little bit late and there was a 5-minute gap in between, let's take the next 10 minutes. Your mom asked, like, how long should the sessions be, blah, blah, blah. And like we can meet for 90 minutes whenever it is that you feel we should meet for 90 minutes. But what I told your mom is past 90 minutes, it's not productive for a kid. It's just I'm testing your attention span, and I don't want to do that. Like you're clearly an amazing kid, an amazing student, but like I don't want to. I don't ever want to hold a session longer than 90 minutes. Okay, cool. So in the remaining time, I saw a couple of interesting things from what you sent me that I'd like to look at. So, and okay. Like, so, this is number 17 on page 342. 17 through 19 it says, but read the instruction for me.
342.
Mm-hmm.
Number 17.
Mm-hmm.
Use definition to define an expression for the area under the graph of f as a limit. Do not evaluate the limit.
Yeah, so the function is, the first one is f of x equals 2x over x squared plus 1. Got it. So talk to me. How, and it's from 1 to 3, so how would you answer that question?
So it's asking for just the expression.
Mm-hmm.
So it's like that big S thing.
Mm-hmm.
With the 1 on the bottom and the 3 on the top.
Yep.
And then 2x over x squared over 1 dx.
There you go. Beautiful. And so let's skip to 19. This is 17. 19?
So it's going to be the S thing,
Mm-hmm.
and then pi over 2 on top and 0 on the bottom.
Yep.
And then x cosine x dx.
There you go. Beautiful. Okay, like this one you can actually do and using Calc AB. This one you need Calc BC techniques for it. So like obviously that's the reason why they just asked you to set it up and not actually evaluate it. You could do this using a calculator or whatnot. So maybe like there's a little bit of calculator skills we could talk about in the future. But sorry. So for now though, this is good. No. So sorry. Like, have you learned about U substitution?
U substitution?
Mm-hmm.
I I feel like I've heard that before, but I'm not sure.
Okay, no worries. So, like the first one, 17, the reason you're able to do it is using a technique called U substitution. So, like, if you haven't learned it, it's definitely a skill you need to have for AB, and it's a skill we need to practice and whatnot. I'll give you a little bit of exposure to it. So, in the remaining time that we have. So, and I'll go back to 17 as like the last thing we execute. So, in full. So, because it requires you substitution to actually evaluate it if you had to. And it is a skill you'll need to know. Anyway, like let's say that I have cos x dx. What's the integral of this?
The integral.
Mm-hmm.
What does integral mean again?
No worries. I just mean like indefinite integral antiderivative.
Oh, the antiderivative.
Mm-hmm.
Yeah, I did not do well in this part of the
It's
test.
okay.
I once there was like the trig functions, I just didn't know how to do it.
It's okay. No worries. So I can help. So these are just ones that you have to memorize. So the antiderivative of cosine. So what is it that we took the derivative of to get cosine?
Sine.
Exactly. So the answer would be sine x plus c. All right, that's nice and simple, and you just need to memorize it. Blah blah blah. Now suppose that I had instead cosine 2x dx. Well, now it's not simply sine x because that 2x right there is a little bit bothersome. So this is what you do. And so this is the very basic of U substitution. So you go, and this is why it's called U substitution. We usually substitute with the letter U. So you go U equals 2x. And then you take the derivative. So that means du is equal to 2dx. And then since we're going to turn this integral to be in terms of u, you need to figure out what dx is. And you figure out what dx is using this equation. And so all we have to do is divide by 2 on both sides. So when we do that, we get du over 2 is equal to dx. Fair?
Yeah.
Okay, now we're ready to substitute. So like we rewrite this integral, recast it in terms of u. So then it'd be integral of cos u, because 2x is u, and dx is du over 2. From our earlier discussion, over 2 is really multiplying by 1/2. So this is really saying integral cos u, and then 1/2 du. Well, we know we could put constants in front of the integral. That's one of the rules. So we could just go 1/2 cos u du. Well, then now, other than, instead of x using u, it's exactly the same as the task that was posed to you earlier, which is the antiderivative of cos u would be sine u. But then there's that 1/2 we've got to keep. So you go 1/2 sine u plus c. But then before you say you're done and you've got the final answer, you've got to go 1/2, replace back, call back what you said was u, which is 2x, and then plus c. Fair?
Yeah.
Okay, so this is like a very basic example, and I will teach you like ways to diagnose like when you should use U substitution, but I'll give you a slightly more advanced example right now, and we will conclude with problem 17. So here's a slightly more advanced example. So suppose that you had instead 3x squared cosine x to the, let me make it a bit more interesting. Cosine 4x cubed dx. Now, so when you get a question like this, the reason why you would know you can do U substitution is this. So when you have a composition of functions, f of g of x, like a composition like that where you have an inside function and outside function, U is usually, and this is a rule of thumb, so it works most of the time. It doesn't mean always. Most of the time, a good idea for guessing, and you are guessing. It doesn't matter if you're an expert at this. You're guessing. And so a good idea for what u is the inside function g of x. And so what am I suggesting should be u in this case?
Cosine 4x cubed.
Sure, cosine 4x cubed is a composition where f is cosine, so g is what?
The 4x cubed.
Exactly. So the inside function is 4x cubed. Yeah, there's this bothersome stuff there, but don't worry about it for a second. So you'd be like, all right, so using this general rule of thumb that we just talked about, I'm going to guess that u is 4x cubed. Got it. Now, just as we had done with this more basic example, at this step, what you got to do is take the derivative on both sides. The left side is just going to say du. What's the derivative on the right side?
12x squared.
That's right. And you mustn't forget your dx, no worries. Then you go like that. And then what is it that we said we have to solve for?
Dx.
Exactly. So how would I do that?
Divide by 12x squared.
There you go. Beautiful. So then so we have du over 12x squared is equal to dx. Now you have your replacement handy for dx. Yeah, you weren't too happy about this guy, but it's okay. Now, you know, I said like you're guessing what u is. So there are reinforcements. Like there are ways to check if you have made the right guess, which is at the stage where you take the derivative on both sides, where you get to the du part, we wrote this. And so the x squared part must be this other stuff. You don't care if they're different by a constant. So the fact that there's a 12 there and the fact that there's a 3 there, we're not bothered by that. But that x squared better have been there. They better have been the same. If that wasn't the case, then you've made the wrong choice of u. So first, you use the rule of thumb that u is usually the inner function. Second, after you take the derivative of both sides and what you claim to be u, then the x power has got to be like matching whatever else is inside of your integral. And you do, at the risk of repeating myself, you do not care about the constants being different. That will just sort itself out. Okay, cool. So we come back now because we've got all our replacement. 3x squared, we didn't have any replacement, so we retain it. And then we go cosine of, and then 4x cubed is what's u, and then dx is du over 12x squared. And then it all works out. Check this out. First, this x squared, and this is why we needed it there. And that x squared take care. And this is why we don't care so much about the constants, because they're just going to simplify into a quarter. So you take out the quarter, write it in front of the integral, and then you go cos u du. Okay, at this stage, just as we had done earlier, just finding the integral of cos u. Well, it would have been the same as doing the integral of cosine of t or any other variable. So you go 1/4 sine u plus c, and then you call back what u is, which is 4x cubed, 1/4 sine 4x cubed plus c. Got it. And this is the final answer. You can take the derivative of this and check that what you're going to get, if you apply chain rule, is exactly this. 3x squared cosine 4x cubed. We could do it. It would have been cosine 4x cubed, and then there's the 1/4, and chain rule would say multiply by the derivative of 4x cubed. That would be 12x squared, and when we simplify this 4 here and that 12 there turn into a 3, we get 3, and if we lead with that, 3x squared cos 4x cubed. That's exactly what's inside here. So there's that. Now, so as I said, I want to, what is it? End with 17. So let's end with 17. What's your faith, if you don't mind me asking?
What's my what?
Faith.
I'm Christian.
Christian?
Yeah.
Yeah. You just mean like I mean I already really liked you, but I just liked you a whole lot more. Like yeah. Like Christ is like literally like the most important thing to me in life. Okay. Yeah. Okay. That's so cool. That's why you came into my life. All right. So if we go back to 17, you set it up nicely for me. That's good enough. Okay. Sorry. Sorry. So that's 2x over x squared plus 1 dx. Okay, cool. And then 1 and 3. So I'm teaching you stuff a little bit ahead. So anyway, we know what to do with the 1 and 3. We plug them in. So let me just abandon that. So remember I told you like a rule of thumb for finding u? Well, that's the inside function. Well, there is no outside and inside function this time. So here's another rule of thumb. U is also usually the denominator. So if you have an inner function, sorry, denominator. My spelling is not as good as my math. um, sorry. So when there's an inside function, outside function, a composition of functions inside of your integral sign, you usually guess u to be the inner function. But when it's a quotient, which is a fraction, then u is usually the denominator. So based on this additional rule of thumb, what are you gonna guess u is?
X squared plus 1.
Exactly. So you claim u is x squared plus 1, and what do you do after?
Take the derivative.
Yep. Go ahead.
Du equals 2x dx.
And then?
And dx equals du over 2x.
Yep. Okay. Great. Okay. So, so you go integral, and then there's 2x here. Well, that guy, remember, we didn't have a replacement for, so we keep it. But then the denominator is what you claim to be u, so u. And then dx is du over 2x. So sometimes it works out exact like this. So then you cancel this and you cancel that. And so you get integral 1 over u du. What's the integral of 1 over u?
The integral of 1 over u.
The antiderivative of 1 over u. It's okay. I can help.
1/2 u to the u squared over 2.
Close.
1/4 u squared.
How about this fella?
Oh.
Yeah, no worries. It's the natural log of u, and so the natural log of u plus c is what you would do if you're doing a general antiderivative, but we know we're doing a definite integral. It's not just an indefinite integral. So we just go ln of u, and then we want to evaluate, so we want to put the numbers we had here. I think I wrote 1 and 3 here. We want to write 1 and 3, but remember, these were for x. 1 and 3 were for x. But we've switched from x to u. So there are two options. One is to go completely back to x, so then we know that the answer in writing natural log of u is really natural log of x squared plus 1. And so then we plug, after we call back u, we can now use 1 and 3 because they're about x. Alternatively, you can also change them to be about u. So 1 and 3. And so if we make them about u, when we plug in 1, you get u equals 1 squared plus 1. That's 2. And so we're switching from x to u. And then for the top, it would be u is equal to 3 squared plus 1. That's 10. And so then that way, you don't have to go back to x. So you could just keep your answer in u, but evaluate from 2 to 10. And so it would be a natural log of 10 minus the natural log of 2. And using our log rules, you can simplify that as a natural log of 10 over 2. That's a natural log of 5. And alternatively, if we went back to x, it'd still be the same. When we plug in 3, we get natural log of 10. When we plug in 1, we get natural log of 2. So we end up at the same place. It's less work if we switch the limits of integration into u. So that's what I'd suggest you do. And the AP will require that you make that kind of recognition, which is like when the limits are also switched to be about u. Okay, cool. Now, so before I end, is Fahey still working there?
Miss Fahey,
okay.
I think she was last year. I have no idea if she is this year.
Okay, cool. All right, who's your favorite teacher there?
Miss Stanek.
Okay, cool.
Yeah.
Yeah. All right, you were amazing to work with. Like, you could not have been easier. Like, you're like very smart, amazing at the fundamentals, an amazing listener. So I I can't ask for like an easier job than working with students like you. So thank you, and we will pick up from here. Let me know if I should give you practice or if you want to practice on your own. This is like your mom asked if you need to send me this material. Obviously, you don't need to send it to me for prep reasons, but I would like you to send me the quizzes and the tests that you had this semester, so I could look through and figure out what it is that we might need to revise.
Yeah. I I don't have any of the quizzes and tests
Okay.
other than ones that are from online. So I
Okay.
have like my past three. That's it. That's
Okay.
just
No.
one.
No problem. You can send me what you have.
Alright. Can you send me some extra practice though?
Absolutely. I'll do that like first thing tomorrow. Okay, bud.
Yep.
Okay. Have a wonderful night.
You too.
Uh
Thank
huh.
you.
You're very welcome.